Welcome back. In this section, we were going to be covering two more new objectives. So we're going to see how to list the names of various changes of states. And what are the changes of states? Solid to liquid, liquid to solid, liquid to gas, gas to liquid, solid to gas, gas to solid. So what are the names of those? Well, let's do a diagram so you can observe those better. Let's assume that we're looking at water. And we're going to start with a ice block. We're going to apply temperature to it or heat. So as we add heat to it, the ice block will become water. We continue applying heat and we get water vapor. So as you can see, we are applying heat. So heat is being absorbed. So going this way, we're going to say that this is an endothermic process. It consumes energy. So the same process can happen backwards, right? So the gas goes to liquid, the liquid goes to solid. For that to happen, you're going to be losing energy, which means this is a exothermic process because you're losing energy. And how do we know we are losing or gaining energy? Well, we can represent the solid like this, right? Molecules are very close together, or the particles neatly organized. We can represent the liquid like this. And we can represent the gas like that. So for these gases to come together, they're going to have to slow down. And when we say slow down, we're talking about the kinetic energy. So they're going to have to lose kinetic energy. So in the process of slowing down, they can get closer together. And that's when we start seeing the intermolecular forces starting to take place. So whenever they slow down and they get closer together, the intermolecular forces is what bringing them together. Because they slow down, the molecule is now have a higher probability that the partially positive will be closer to the partially negative, and therefore they come together. As they slow down even further, then the intermolecular forces really takes hold, and the molecules come together and start forming a network. So solid to liquid to gas, all those are endothermic process because they require the molecule to gain energy. And how do we know they're gaining energy? Well, let's take a look. Like I said before, the molecules here are very close together, which means they're properly oriented so that the partially positive, partially negative are coming together. And you can see the trend. So what happens when we apply energy to it? When we apply energy to it, the molecules begin to vibrate faster. And because they vibrate faster, instead of you having a perfect connection like that, because they're moving, you can end up with something like this. And you can see now they are not properly oriented because they're moving like crazy now. And that attraction is broken apart. Therefore, the molecules can separate and they can go from a neatly organized system into something more random. So that's where the energy comes into play. That's how we know that it is endothermic process absorbing energy or exothermic process releasing energy by thinking about increase in energy, increased kinetic energy, molecules are moving faster, they are no longer, they can no longer maintain the perfect orientation of partially negative, partially positive. So intermolecular forces are overcome, the molecules separate. Solid to liquid, liquid to gas. So if you always think like that, you should be okay. Well, let me give you some guidance so you can use this diagram. So we know we have this. So we know we have the solid, we have the liquid, and we have the gas. So we're gonna call this melting, while we're gonna call this one freezing. And I'm gonna represent the absorbance of energy via this darker color and the release of energy by the blue color. And we're gonna call this sublimation. We're gonna call this deposition. We're gonna call this boiling. And we're gonna call this condensation. And this is something that we cover, and hopefully everybody covered with your respective professor back in 1411. And both melting and freezing for water, both melting and freezing for water at 1 atmosphere of pressure happens at 0 degrees Celsius. So at 0 degrees Celsius, when the solid is changing to liquid on water, the solid and the liquid are in a perfect equilibrium, and both of them are at 0 degrees Celsius. The boiling and the condensation are happening at 100 degrees Celsius. So those are things that you need to remember. Every time I say condensation, 100 degrees. Every time I said boiling, 100 degrees. The same with that. Sublimation and deposition do not happen for water, not for water, but I wanted to show it to you anyway for any other substance. So that diagram is for general for anything, but sometimes at 1 atmosphere of pressure, sometimes it doesn't happen. So this doesn't happen for water. If it was dry ice, then you will see that process. Another thing that I want for you to be aware of, the energy required for this process to happen, that's what we call enthalpy. And we represent it not as enthalpy, but as the change in enthalpy. And for this particular process, freezing or melting, for both of them, the energy required for that to happen is going to be the enthalpy of fusion. The energy required for the boiling or condensation to happen, we're going to call it the enthalpy of vaporization, and that's given by the amount of energy required by the amount of substance, either on grams or moles. So remember that diagram, that will be helpful. So that's what we're going to be talking about. This is just an introduction. So that's what we're going to be talking about when we're talking about changes of states. And you can see now why they are endothermic and why they can be exothermic. We're also going to be talking about heating or cooling curve, which is a graphical way to show exactly what's happening with matter as matter absorbs or releases energy. And that's going to be based on the energy, basically the enthalpy changes in relation to the phases. So let's go ahead and do these two objectives. And we're going to do it like always with a problem. So let's do this problem. The human body obtains 1,065 kilojoules, and you know from Chem 1 that that's a unit of energy, from a candy bar. So if I eat a candy bar, that specific candy bar, I'm gonna get that much energy out of eating that specific bar. And it's probably even on the label. If this energy were used to vaporize water at 100 degrees Celsius, so I'm exercising and consuming energy, and that amount, and we are assuming that amount of energy is vaporizing water from my body. Basically, I guess like sweating, not exactly like that, but like that. And vaporize means going from liquid to gas. So that's boiling, and we're gonna need the enthalpy of vaporization. How much water could be vaporized? So based on that energy, how much water could be vaporized? So like I told you before, these changes of state require energy, and the energy is usually given in the form of enthalpy. And we're talking about vaporizing water. So we have a table with values, and we have water here. And as I told you before, the enthalpy is going to show either for boiling or condensation, or for freezing or melting. On this case, it's just showing you the delta H of vaporization when the molecule is right at the boiling point, and it also shows you the delta H of vaporization when the molecule is at room temperature. So at the boiling point, the molecules that's 100 degrees Celsius, so the molecules are moving faster already. So to go from liquid to gas, all they need is a little more push. So that's why you see the difference in energy. If I begin at 25, it's going to require more energy to get it first to the point where they are at the boiling point, and then to push it to go from liquid to gas. So on this particular case, we're dealing at 100 degrees Celsius, which is this one at the boiling point. So that's it. That's why it's important that you know the temperature at where the phase changes are happening. So this is telling me that this is vaporization, and it's also working here. So the delta H that applies on this case is 40.7 kilojoules per mole. And in this particular case, we're talking moles of water, right? So how do I do this problem? Well, there's a formula that tells, like you see on these units, that the energy relates to the amount. So there gotta be a formula that allows me to take that value, which is a conversion factor, right? 40.7 kilojoules for every 1 mole of water, and just tell me how much water is that. So how many moles? So the formula for that is Q, which is the amount of energy, equals the amount. This could be mass in grams, or that could be the amount in moles, depending on the delta H that we're using. And in this particular case, we're using 40.7 kilojoules per mole, because the formula we are using is heat equals amount of substance times the delta H of vaporization. So what it's asking us is how much water. It's asking us to find the amount. And it's telling us that the energy required to vaporize it, or it's asking us to find the amount that can be vaporized when this energy is required or used. So basically what it's telling us is Q, which is the energy, is going to equal the amount times the heat of vaporization. And we're talking about water on this case. So at this point, you have mastered the chemistry of this problem. You understood that the amount of energy is going to be equal to the amount of substance times the energy required to vaporize it at 100 degrees. And you were able to equate, oh, so this is my energy. This is the value I need at 100 degrees. And all I have missing is the amount. So all you're going to do is algebra from this point on. So the mass is going to be equals to 1065 kilojoules divided by 40.7 kilojoules per mole. When you do the math, this cancels, and now you're going to have moles is going to equals 1065 divided by 40.7. And once you do that, you know how many moles of water you have. But that's not the end of the problem. So let's see how much that is. So let me calculate it real quick, just a second. So if I do 1065 divided by 40.7, I get 26.2, three significant figures, moles of water. But that's not what the problem is asking. Let me clear the screen a little bit. So we know we have moles of water equals 26.2. So, but that's not what the problem is asking. The problem is asking how many liters. And it gives us the density. So if I want volume, I need the grams, right? So I know that if I have 26.2 moles of water, and I multiply that by the molar mass, I should be able to get the grams. And once I get those grams, which is gonna be 26.2 multiplied by 80, that's gonna be 471.6 grams. Once I get those grams, given that I know the density, and the density is 1.0 milliliters for every 1.00 grams, that will give me the milliliters. And since we multiply by 1 divided by 1, I'm getting that I have 471.6 milliliters. And from here on, it's just a matter of changing this to liters. And there's 1,000 milliliters in one liter. So 0.472 liters would be our answer. And according to the problem, we got three significant figures based on our original link from problem to problem. So that would be the answer to this problem. So what's important about this problem? The most important thing was the use of the formula that you just learned. This is not from Chem 1, this is something you knew already, something that you didn't know. So which is the energy on a phase change is gonna be given by the amount. It could be grams or it could be moles. On this case, we have a vaporization, which corresponds with enthalpy of vaporization. And on this case, is given on kilojoules per moles. Therefore, this here on this particular case, it's going to be moles. Sometimes you're going to see kilojoules per grams. So on that case, you're going to need grams. So you learn the use of that formula. Converting the moles to grams, that's 1411. Using the density, that's 1411. The only new thing you learned was the use of this formula. So email me if you have any questions, and you know all the other resources you have. By the way, as you work through this course, if you look into Canvas, it tells you the chapter that you need to read. It's strongly recommended. You have a bunch of tutorial videos. You have my lectures. So you can do all those three. So you can just pick the one you works better for you, and then use the other ones as reference. The lecture is the only one that I really want you to do because you have to complete the daily work. And the daily work is coming from the lectures like this one. So this is your first daily work for this part, but you're putting all of them together, A, B, C, D, and whatever else I do, in only one paper before submission. So this is the daily work as we continue going through it. And you can put it on pause and work on it later. Another problem. What mass of water can be evaporated? So evaporation means a change of state. So that means either you're going to use delta H of vaporization or delta H of fusion. But clearly, this is evaporation. So you're going to use delta H of vaporization. So what mass of water can be evaporated with the energy released from a 5 grams block of iron when its temperature goes from 250 degrees Celsius to 100 degrees Celsius? Assume all this energy that is coming out of this block cooling down is used exclusively on the vaporization process. So this is a lot. So the way I like to do it is by drawing it. So what is this is asking? I have a block of iron. This helped me visualize it better. And this block of iron weighs 5 grams. And this block of iron at this particular time is at 250 degrees Celsius. And it's going to lose energy. And every time we're talking about heat or thermal energy, we're going to use Q. And it's going to go from its original state it's still going to be 5 grams. That's not going to change. Nothing is happening to the block besides losing energy. And it's going to end up at 175 degrees Celsius. So that's what the problem is saying. I have a block of iron at 250 degrees Celsius. It's going to be losing energy, and its temperature is going to go to 175. Excuse me. And the question is, if all that energy that comes out goes into a water to vaporize it, how much water can I evaporate? So this requires thinking in a different way. We know that this is a change of state. So most likely we're going to use the formula mass times delta HV equals heat. It's asking to determine the mass of water. So that's what we're looking for. The mass. And we're talking about water. And it doesn't tell us anything about the state of the water. So let's assume that it's already 100 degrees. So I'm going to use this value for the water, kilojoules per mole. And it's asking for the mass of water. So mass is grams. So I'm going to say that Q is going to equal the mass times 40.7 kilojoules for every 18.0 grams. Where is that 18.0 grams coming from? Well, according to the table, these are kilojoules per mole. So how much is 1 mole of water? 18 grams. So that's what I did. Instead of putting 1 mole, I just put it in grams already, so that way these will be grams. So the question is, if I'm looking for the mass, I cannot have another unknown variable. I need to know what Q is. What I'm looking for should be the only unknown variable. So I need to know what Q is. Question is, how do I find Q? Well, the heat is coming from the block of iron, so whatever energy the block of iron releases, that's the energy that the water is absorbing. Imagine you have the hot block of iron, and you put water on it, and the water evaporates. So how can I find the Q that is coming out of the block of iron, which should be the same as the Q that the water is absorbing? The hot body releases energy, the colder body absorbs energy. That's from 1411. So how can I find that Q? Well, I'm going to go back to 1411. On 1411, this is the formula you learn. You learn on 1411 that you can calculate the amount of energy absorbed or released by a substance by knowing how much you have, knowing how much energy that substance is capable of absorb, the specific heat, and the change of temperature that it happens when it loses or gains energy. So given that, I can find the Q of the iron block by using that formula. So I think we're done with the drawing already. So the Q, or the heat that the iron block releases, is going to be given by the mass of the iron block, which is 5.0 grams, multiplied by the change in temperature, is going from 250 degrees Celsius to 175 degrees Celsius, multiplied by the specific heat of the iron block, which is given here, 0.50 joules over grams. So the grams are going to cancel. Degree Celsius. The degrees Celsius are going to cancel, and the only remaining unit is going to be a unit of energy, which is right, because that's what I'm looking for, energy. So when I do this operation, my result is going to be, just give me a second, 5 multiplied by 250 minus 175 multiplied by 0.450. So that's going to be 168.8 joules. So that's how much energy the iron block is releasing. That same amount of energy is what is being absorbed by the water to be vaporized, which is going to be the mass times 40.7 times to the third, that's the kilo, joules, divided by 18.0 grams. So at this point, all I have to do is solve for M. So 168.8 joules multiplied by 18.0 grams divided by 40.7 times 10 to the third joules, or 40.7 kilojoules, 10 to the third means kilo, equals mass. joules cancel with joules, and the resulting unit is grams, which is a unit of mass. So that should be okay. So mass equals, just give me a second to calculate that. Mass will equal 168.8 times 18 divided by 4700, 40,700, which is going to be 0.075 grams. So that's how much you can evaporate grams of water by a change on temperature of 75 degrees on the block. In other words, if you put 0.075 grams of water on a block that is 200 degrees Celsius, by the time all the water evaporates, the iron block is going to cool down to 175. That's what that means. And you can see how this can have a lot of applications on an engineering problem. When you're trying to determine how to cool down, how much substance to use, and so on and so on and so on. So let me know if you have any questions on this. So that would be your daily work for that particular problem. So reviewing real quick. Remember, the Q of the hot body, in this case the block of iron, is going to be the same as the energy that the water absorbs. The temperature of the block of iron is going down. For that, it has to release energy. And for something to be vaporized, you have to absorb energy. Remember from 1411 that energy release is negative, energy absorbed is positive. And then you already know how to use the formula Q equals the amount times the enthalpy of vaporization or fusion when you have a change of state. So you only use this formula when you have a change of state. You only use this formula when the temperature is changing. Remember that I told you that on the change of state, freezing and melting, both of them having a 0 degrees Celsius. So there's not change in temperature when you go from solid to liquid or liquid to solid. To get to that point, that's when there's a change in temperature. So different formulas, two formulas that you're going to be using. One for whenever you're warming or cooling something, and the other one when the actual change of phase is actually happening. So here's your 12.9. Sorry, 12.9, give you a second so you can have a capacity of pausing it without having to run. That should be enough. And here's another problem. How much heat is evolved? So once more, we're talking about evolving or releasing. So we know we're going to find minus Q, heat that is being released. In converting 1 mole of steam, so we have gas, steam is water, and it's on a gas state, and you have 1 mole, which is the same as 18.0 grams. So evolve, and we want it to be on kilojoules. So that's what we're looking for. 1 mole of steam at 145 degrees Celsius. So this is really hot. It's way past the boiling point. So you evaporate it, made it into gas, and you continue warming it up all the way to 145. So that's already done. And it's going to go from that temperature, it's going to go all the way to become ice. So that's what I call translating the problem into a visualization. And the ice is going to go not just to freezing, it's going to super cool down below freezing. The heat capacity of steam is 2.09. The heat capacity of ice is 2.03, and the heat capacity of water. So we're talking about liquid, solid, and gas. So when the water is a gas, the molecules are already moving faster. They already have a bunch of energy, so they can only absorb a little bit more. When the molecule is a solid, or a liquid in this case, on a liquid, water is a little bit weird. So when the water is liquid, then you have a lot of hydrogen bonding happening. The molecules are closer together. Water is one of the very few substances where the solid state is less dense, or they're not as close together as in the liquid. That's why this is higher. So depending on the particular state of matter, the amount of heat that they can absorb, or the heat capacity, changes because the molecules have more or less energy already on those states. So it's not the same for every state. And the heat of fusion, delta H of fusion, freezing or melting, is this much. And the heat of vaporization, boiling or condensation, is this much. And it's asking us to draw and label a curve. So that's new. Draw and label a curve. So let's get organized first. And you know, you're familiar with water. You have been on this planet for several years now. You know this planet is 70% water. Your body is about 70% water. So we know a lot about water. For example, you know that water goes from from solid to liquid and then to gas. Water doesn't go from solid to gas like dry ice does. So what is a curve? On this case, we're starting at 145 and we're going to minus 50. So it's cooling down. So this is a cooling curve because it's cooling down. The process is cooling down. So we're dealing with a cooling curve. And a cooling curve is nothing more than representing the process in a graphical way, where you have temperature going up on the y-axis and heat being released on this case. So this is an exothermic process on the x-axis. And let's say that we start at 145 degrees Celsius. So at this particular point, that's where our graph begins. But we know water. We know that water boils at 100 degrees Celsius. So at 100 degrees Celsius, that's when you have a change of state. So as we release heat, it's gonna go down to 100 degrees Celsius. So the temperature is gonna go down. So at 145, some heat has been released. At this point, some more heat has been released. And it makes it up to this point. And we know that at 100 degrees, there's a phase change. And vaporization or boiling and condensation happen at 100 degrees. So there's no change of state. So at this point, the temperature does not change. That's what we call a plateau. A plateau represents a change of state, and during the change of state, the temperature does not change. So therefore, the temperature remains constant, but heat continues to be released. So once all the gas have become, so this is the gas above 100 degrees, and here you have gas and liquid on a perfect equilibrium, and this is happening at 100 degrees Celsius. Once all the gas has condensed into the liquid, then the temperature continues going down until it reaches what temperature? You know water, so you know that at 0 degrees, there's another change of state, another plateau. So this is liquid. Here you have the liquid on perfect equilibrium with the solid, and that's happening at 0 degrees Celsius for water. And after that, you can continue cooling the ice. And on this particular case, we're gonna make it all the way to minus 45 degrees Celsius. So, ladies and gentlemen, we just finished drawing a cooling curve. How did we do that? By knowing when the different changes of state happen. For water are 100 degrees and 0 degrees, knowing that at those particular points, it's going to take time, but the temperature is not going to change. So therefore, we developed a plateau. So those are my plateaus. And then the temperatures continue going. Since the temperature is going down as heat is being released, you end up with the diagonal line. So we have drawn and labeled our curve. And from here down, all this is solid. So all this area here is solid. So this is gonna be our solid area. This is gonna be our liquid area. Let me use a different color. I'm colorblind, so I have to go darker so I can see it better. So this is my solid. This is my liquid area. And then this is my gas area. So we have drawn, we are done drawing the curve for this process. Identify each segment. We have done that also. Exothermic or endothermic? Since we are cooling down, any process going that way is gonna be exothermic. So if I ask you going from gas to liquid, endo or exo, you say, well, going from gas to liquid is this one. So that's gonna be exo. What about going from solid to liquid? From solid to liquid, I'm going on the opposite direction. So that's gonna be endo. What about going from minus 20 to 0? Well, you know that you are applying energy, so that's gonna be endo. So we have done all that. So the only thing that we have remaining is calculate Q, or the heat required in kilojoules, to go from 145 to minus 45. So how do we do that? Let me go ahead and clear the screen a little bit. So how are we gonna calculate that? The way we're gonna do that is by knowing the formulas that we can use to find Q. You can find Q by doing the mass times the heat of vaporization. You can find Q by doing the mass or the moles times the heat of fusion. And you can find Q by doing the mass times the change in temperature times the specific heat capacity. Let's call this formula number 1, formula number 2, and formula number 3. And what I'm gonna say is, for this particular section, from here to here, the temperature is changing, so I'm gonna have to use formula 3. For this particular process, the temperature doesn't change, so it's gonna have to be 1 or 2. However, what's happening here for water is going from, it's 100 degrees, So that has to be boiling or vaporization. So I'm gonna be using number 1 only. So number 1 is what I'm using for that particular section. For this particular section, the temperature is changing again, so I'm gonna be using formula 3. For this particular section, the temperature doesn't change, so I can only use 1 or 2, but this is going from liquid to solid, that's freezing, so I'm gonna have to use fusion. Fusion is the one that is used for freezing or melting. And then for this particular case, I'm gonna have to use formula 3 again, because the temperature is going from 0 to minus 45, so the temperature is changing. So the question is, when you use formula number 3, you're gonna have the mass. And how much is the mass? 1 mole. So we know the amount. So 1 mole of steam equals 18 grams. So we know this is gonna be 18.0 grams, 1 mole of steam, which is water. The change in temperature, for the first one, the change in temperature is 145 minus 100. So that would be the change in temperature for the first section. For this one, the change in temperature is going to be 100 degrees Celsius, from 100 to 0. And for this one, the change in temperature is going to be 45, from 0 to 45. And then you're going to multiply by the specific heat. For the first one, we're dealing with a gas, right? So for the first one, you need to find the specific heat for the gas, which is going to be right there. So that's what you do for that part. For that part, just plug the numbers. The mass is 18 grams, 1 mole. The delta T is going to be 45 degrees Celsius, from 145 to 100, and the heat capacity for the gas. That's why it's so important that you draw the curve first, so you know exactly what you're dealing with. So I'm not going to do all the calculations on this one. I just want you to realize that once you label everything on the curve, then you have to be thinking, what specific heat do I need? What formula do I need? And then you calculate each Q, and then you add it together. And that will be how you find the heat in kilojoules for the whole process. So let me know if you have any questions on that. And these are the questions that you can ask me on email, or you can bring to the workshop when we meet. And that will be the daily work that you will do. Once more, draw and label a cooling curve for this process. Identify each of the segments. Determine if it's exothermic or endothermic, and then calculate the heat or the Q for the whole process. Find each Q with the proper formula and add all of them together. And that's what we're going to stop for now. When we come back to the last, to the last video, we will cover then two more new topics. So see you later. Go check the textbook. If you have any questions, check the tutorial videos. Email me. Go to the Science Learning Center, whatever you need to do. Remember, this is a blended course. The responsibility is on you to go find the knowledge. I'm here to coach you and guide you. See you soon.